Good afternoon, everybody. My name's Charlie Nicklin. I'm the Chief Executive of IAgrE. I'd like to thank you all for joining our April presentation. I'd like to welcome Dr. Tom Walters from the Small Robot Company for our lecture today. Tom is the Chief Technology Officer at SRC and joined the company back in 2011. Tom has a background in applied machine learning and previously worked as a research scientist at DeepMind in London. Tom's presentation today is going to take us through some of the technology being employed that enables SRC's robots to gather acres of field crop data on a per plant scale. So that should be really interesting. As usual, everybody is muted. If you would like to ask questions, please use the chat function at the bottom of the screen, and then at the end of the presentation, we'll unmute you so you can ask in person. Okay, I'll now hand over to Tom.
Thanks very much, Charlie, and thanks very much for having me. I think hopefully this will be of some interest. I think it's kind of strays kind of very much into the realm of machine learning, but with sort of a clear application to agriculture, and kind of using our robot, the Tom robot, as a sort of basis for gathering data and providing insights. So I'll just start my presentation. Yeah, I've kind of called this "Enabling Per Plant Prescriptions with Robotics and Artificial Intelligence," which is a bit of a mouthful for a presentation title. But the idea is that we have a fleet of robots which can traverse an entire field, covering an area of sort of around 20 hectares or so over the course of a day, and these robots survey the field at extremely high resolution. And this high resolution imagery allows us to provide really very detailed insights to the farmer about what's going on in their field. And the way that we do that is by analyzing all of the images which are captured using a selection of different models, which are kind of optimized for detecting individual plants, be those crop plants or weeds, or whatever it might be. So the Small Robot Company is on a mission to feed the world while regenerating the planet. So we're really interested in this idea of being able to move agriculture onto agriculture on a much more sustainable footing. And we believe that the way to do that is through providing these insights to the farmer at extremely high resolution in their field. So we want to be doing stuff that is at the scale of a field, but ultimately treating the field at the resolution of individual plants. So we know that current farm technology is wasteful. Farmers have to apply inputs to their whole field at a time, and chemicals accumulate in the soil. We have kind of issues with chemical runoff and all of these other things. And the way that we believe that that we can mitigate many of these issues is to provide this per plant view of the field, to kind of improve the efficiency, choose exactly the right areas of the field where chemicals need to be applied, to treat each plant individually rather than treating the field as a whole, and to be kind of dealing with ultimately much sort of smaller pieces of equipment in the field as well, which produces things like soil compaction and so on. So there's many kind of benefits to trying to be able to provide this plant level resolution data to farmers. So we believe that ultimately, by understanding every plant in the field, by optimizing the care of those plants, we can reduce this chemical use, reduce waste, reduce emissions, and improve biodiversity. Based on our current data, what we've seen so far over the course of kind of the couple of growing seasons that we've been doing this already at scale, we've seen kind of significant reductions in the amount of fertiliser that farmers need to put onto their fields by targeting the fertiliser correctly, by reducing the amount of herbicide significantly by only targeting areas which are particularly weedy, for example, and sort of overall reducing input costs. And we believe that we are sort of on a journey to kind of continually improving this data and improving the level of what we can do here. So we believe that the savings to the farmers are very significant. This is just a little video showing kind of what the robots look like. This is our workshop at Porton. And we have an example here of one of our version 4 robots. This is the Tom robot, which is set up for surveying a field. So the robot has a boom with a series of cameras spaced along the boom, and it will run over an entire field, taking imagery with those cameras. You can see that there's a little flash that goes off each time an image is captured to try and get the lighting kind of very accurate and very, very consistent across the across all the images. And so this is the kind of image that we end up getting from one of these cameras. The resolution of these images is such that we can sort of see right down to the individual kind of cotyledon stage weeds, and we can detect each of those individual plants in the image. Then we kind of we process all of those data that come back from the robot to field scale maps, which show, for example, in this case, detections of weeds at the scale of field. And from that, we can do things like generate treatment maps for existing farm machinery. For here, for example, that was a treatment map for a sectional controlled sprayer, which allows us to kind of spray maybe sort of 3 metre by 3 metre or 1 metre by 1 metre patches of the field and apply the chemicals only where they're needed. So spot the weeds and then spray them and put the spray where it's actually going to be of value in getting rid of the weeds. So the platform itself is sort of designed to be very modular. We built a series of iterations of this robot platform over the course of the last few years, which have kind of culminated in this version 4 robot, which is specifically designed to be extremely modular and extensible. So at the moment, what we provide in the field is a kind of the surveying service, but the kind of individual kind of blocks of the robot can be split apart easily to kind of to support other payloads in the middle. And so kind of, you know, the vision ultimately is to move on to having kind of field scale things like non-chemical weeding being provided by this robot. So just to summarize kind of what we saw in that video, we have the robot with the ability to kind of go and scout an entire field. It has a series of 8 cameras along its boom, which cover kind of the entire sort of area, allow us to image the entire area just in front of the robot. Those have a pixel density of 0.28 millimeters per pixel. So that means that we are able to really get imagery of very, very small small plants in the field down to the level of kind of, you know, individual tiny emergent stage weeds. One of the sort of crucial design features of this robot is it has very low ground pressure. We're deliberately trying to run this robot in scenarios where it can run over the crop up to sort of later growth stages. So the ground pressure is kind of about a third of that of a human foot on the ground. And as I mentioned, it's a sort of modular platform which allows us to sort of split out sections to allow us to put in different sensors, to put in kind of spraying capability, weeding capability, and so on. So, as I mentioned, the goal ultimately is to move to per plant action, where we can take this plant scale, this plant resolution data, and then be able to act on each plant individually, and only treat the plants that need treating. The image on the left you can see there is an example of us a prototype non-chemical weeding robot that uses a bolt of electricity to try and to remove weeds. And so it goes and targets the individual weeds in the field. So in this case, what we do is run a survey over the field, find sort of geolocations for where the weeds are, and then take an action robot back to that same point and then apply the action. In this case, we zap the weed with electricity. So the goal here ultimately is to be able to, in this case, remove the chemicals entirely from the operation, that we don't need to actually apply herbicide to this field because you can go and take individual weeds and target them individually. So that's the vision. And now I want to kind of go into the details of the technology that we're using to provide this. Now, my background is in machine learning. I have previously worked on large scale audio, video, image processing systems. And so this is sort of, for me personally, this is a very interesting area because it kind of allows kind of outlet for that interest in large scale machine learning systems, but on a problem which is of genuine and significant benefit to the planet if we get this right, if we can kind of make this whole system work end to end and significantly reduce the amount of inputs required to do agriculture and make it more sustainable. That's something which really excites me. So the robot has gone through multiple iterations over the course of several years. You can see here kind of the progression of our version 1, version 2 robots, which were sort of developing this concept of being able to go and survey a field at extremely high resolution. The version 3 robot, which you can see in the top right there, is the robot which we've been running in fields until fairly recently, and has been now replaced with the version 4. And then this is the kind of the state at which we got to, where we were able to kind of go out and survey an entire field with 6 cameras working at high resolution. The version 4 is another iteration of that, with sort of significant improvements on the design, making it more modular, making it more scalable, easier to produce at large scale, and sort of more robust and more modular as well. Now, a question we get asked a lot is, why are we using robots on the ground rather than drones, for example? Obviously, kind of you take a drone and fly it over a field, and potentially you can hover a drone fairly close to the ground and sort of get high resolution imagery. But if you sort of run the numbers on that and look at the operational requirements of the drone, in order to run a drone over an entire field at that low level that you'd need to get high resolution imagery is really prohibitive in terms of time and kind of number of battery changes required, and many other things. Also things like weather conditions and wind, for example, could be a real issue. So essentially, the robot allows us to have this really stable platform where we have lots and lots of control over the imagery that we're gathering. The robot can run in many different weather conditions, and has kind of this light which allows us to control the exposure, so we get consistent imagery across an entire field. The alternative, another alternative would be to sort of mount cameras on a tractor. Tractors tend to run very fast through a field, so this is kind of it's difficult to get the kind of quality of imagery we need when you're moving at kind of 14 kilometers an hour or something in a field. So this is kind of a the robot again allows us more control. You don't have to. It's not bumping around or kind of pitching pitching more than you want to get the kind of imagery that you need. So let's talk about the data a bit. So we have these images from the robot. These are some example images from a real field where we've got winter wheat crop growing. You can see sort of that you get the individual rows of wheat plants are clearly visible in that. And we ultimately analyze all of those images gathered by a robot through a number of different systems. So we have systems for detecting weeds, broadleaf weeds, for counting crop plants, and so on. And so we're looking at gathering of the order of maybe 1 to 2 terabytes of data over the course of a survey in a field, and that's sort of several 100,000 images from a survey. So this is a significant amount of data and a significant amount of processing time. The end result of what we get are these extremely high resolution maps, which show sort of the exact, in this case, the exact weed burden in your field, and these hexagons which are showing here at the level of kind of they're roughly a square meter in area, those. So this is a useful level of resolution to be able to kind of present the data out for a whole field, but obviously the data backing this up is even higher resolution. Another interesting application for farmers is variable rate nitrogen application on fields. So here we have models which detect the individual crop plants, and at an early growth stage we can see kind of the location of those individual plants, and then We also do a sort of biomass assessment by looking at the green area in the field, which gives us this green area index, which essentially is kind of like a proxy for the amount of plant biomass in the field. We can combine those two bits of information, the crop plants and the biomass assessment, and sort of have a set of algorithms for how we combine those to produce a treatment map for how to apply nitrogen in the field, or recommendation of how that can be applied. Now that it's possible to generate that at extremely high resolutions, down to the resolution of the individual plants. But obviously the way that can be used with current equipment is at slightly lower resolution. So typically, if you have a sectional controlled sprayer, it might be working on a sort of 1 meter by 1 meter resolution, or maybe even a 3 meter by 3 meter resolution. But as we move to kind of more and more fine-grained application techniques, treatment techniques, these maps become of even more value to the farmer. So I'd like now to sort of take a step back and talk a bit more about the technology that we're actually using to do this, and how we are able to process kind of a field's worth of data at this resolution. So as I mentioned, we have this boom on the robot, which is taking images with all of the cameras kind of in a line. The robot moves at a sort of uniform speed through the field as much as possible, and we can sort of choose when to fire the cameras to get uniform overlap between those images. We typically kind of have enough overlap to ensure that we're going to be able to cover the entire field and cover everything, but not so much that we end up with sort of lots of copies of the same area of the field. In parallel with the image capture, there's also a high resolution GPS unit on the robot, which is capturing the GPS location of the robot boom, the center of the boom, and we can kind of correlate those two data sets afterwards. So the GPS track with kind of fine-grained timestamps, and the timestamps we have on the images allow us to give us extremely high resolution, high spatial resolution on geolocating those images. Each image can then be processed through a set of these object detection models, which gives us a location of the plant within each individual image. And then we can sort of do things like take into account overlap between images and kind of remove duplicate detections and so on, and then kind of filter out the set of detections which we're interested in. The way that the machine learning models work behind the scenes is we have our set of raw images from the field. We have a vast amount of images coming in from the field, as I mentioned, sort of hundreds of thousands of images coming in from a typical survey. As we do surveys, we gradually build up a data set of labeled images. So we will choose some subset of images from each new field that we go and survey. And experts will use a labeling tool where they're essentially drawing boxes around the plants of interest in an image. So kind of drawing a box around the individual wheat plants, for example, or selecting broadleaf wheats. That gives us a data set, an ever-growing data set of labeled images, which is what we need to be able to train our object detection models. So we end up with these images and sort of a bounding box essentially around each of the plants of interest. Now, there's a vast and ever-increasing sort of set of models, machine learning models, which are available for doing object detection. And the wonderful thing about sort of the way that the machine learning kind of world is moving at the moment is that there's an enormous research community around the world who are actively kind of working on improving the performance of all of these models. So sort of everything from object detection to sort of audio processing, and is an area of huge research right now. And it means that we have an enormous sort of set of potential candidate models to be able to choose from and can kind of track the state of the art. So as an example here, I've got this RetinaNet model, which has served us very well for a number of years as an example. This is an object detection model which takes the raw image pixels as input and has a series of neural network layers which sort of lie on top of that, which perform various sets of operations on those raw pixels, with the ultimate goal of predicting the location of these bounding boxes. So essentially being able to recreate what a human annotator has done by drawing boxes around the individual plants. So the process of training one of these models is to take your annotated data set. So this is your data set that was annotated by human experts. And the model essentially starts off by just seeing the image pixels and taking a guess as to where the bounding boxes should be. Now, obviously, when the model starts doing that, it essentially has no knowledge of what images look like, or where bounding boxes, or what the weeds look like, how they should be working. And the process of training one of these models is essentially one of helping the model to become a little bit less wrong about how it's predicting things as it goes through multiple iterations of training. So, I mean, I won't go into all the details about how this works, but essentially the model consists of a series of layers where sort of, you know, the value of the color of individual pixels is encoded as a number, and those can be combined in various different ways by kind of basically taking weighted sums of different areas of the pixels in an image. There are a number of things like kind of convolutions which you can perform over images. So, for example, you can take some sort of function, what's known as a kernel function, which you can then run using a convolution over an image, a two-dimensional convolution, which gives you a sort of a map of a map at some resolution of the image, and kind of like where particular patterns, for example, have been seen in that image. Now, all of the numbers associated with sort of the weights with which you add pixels together, the way in which you kind of combine your information, all those numbers are things which can be learnt by the model. They're called the parameters of the model. And the way the process works is you have the model make a prediction. It goes forward. You takes an image and says, okay, given this image, I think that there should be a bounding box at this location. And then you use the information you have, the ground truth information you have from your annotated images, to be able to say, was that right or wrong? How right or wrong was that? So if the bounding box that the model predicts for example, a weed overlaps with the bounding box that a human expert predicted for the weed, then you can say, then you can give the model a sort of a positive score, essentially. There is what you compute what's known as a loss function for an image, which says kind of like essentially how right was I about my predictions. And the way the models are set up, it means that in addition to being able to go forward through the model and say, okay, the model sort of has made these predictions, you can then use your understanding of how you were wrong to basically try and tweak the values of those individual parameters in the model to make it a little bit less wrong. And that's called backpropagation. So there's a vast amount of sort of literature on this, and which goes back many, many years. But the crucial thing is that it's a process which only becomes possible when you have enormous quantities of data. And the interesting thing about sort of the explosion of machine learning in recent years is that a whole load of techniques which were developed decades ago, even for performing these sorts of operations, suddenly became possible to possible to achieve really, really good quality results with these sorts of techniques, because we suddenly had the scale of data sets we needed and the amount of compute required to actually train models which are able to sort of learn something significant about the world. And that's kind of, you know, what essentially we're sort of riding on the coattails of here is this enormous, great kind of wealth of research which has happened in this area. So, sorry, a bit of an aside into my my sort of my previous life, but I think it's kind of interesting to understand, you know, how these kind of these techniques, which initially started off as kind of like very kind of abstract, academic kind of ideas, about how machines should learn, up to like essentially kind of modeled on how human brains learn, how those have become a kind of a genuine and useful tool for doing a whole range of kind of applied problems in the real world. So that's the machine learning models. Now we need to talk a little bit about the sort of all the infrastructure that goes with them. So the pipeline we have for processing these data sets is kind of one which has to scale to very, very large amounts of data. So we have our raw data sets from the field, which run to terabytes of data, terabytes of raw images. These are stored on drives on the robot as it runs over the field, and then at the end of a survey, the drives are extracted and basically uploaded to the cloud. We have the option of either processing stuff on site using a local server, or if we have enough internet bandwidth, then running the processing in the cloud. And then that's the point at which we are able to kind of really sort of scale the processing horizontally. We can run multiple machines in parallel, sort of processing individual bits of the field, running these detection models on some subset of images, and then sort of stitch together essentially a map of the field based on all of those individual areas which we've done. Now, in order to run the kind of these object detection models, especially, we need to be able to use GPUs. So that's kind of essentially graphics cards, but which are capable of performing the kind of mathematical operations that you see in these deep learning models, these machine learning models, perform very quickly. And graphics cards, GPUs, are exceptionally well suited to this sort of computational problem, because it turns out that it's essentially mathematically very similar set of operations to what you're doing when you're trying to compute 3D scenes. It's lots and lots of matrix mathematics, lots of kind of performing the same operation multiple times on different data, which is something which GPUs are particularly well suited for. So we can make use of the fact that that sort of cloud providers like AWS and so on have banks of these machines available, which you can essentially rent for a short period of time to perform your individual processing, and don't have to worry about the rest of the time. So the sort of interesting thing about the data is that obviously while we gather something of the order of kind of a terabyte or two of raw data from a field, really the treatment maps we end up producing for the farmer and the sort of like the visualizations are ultimately just distilling out of that kind of like a few megabytes worth of sort of like the valuable insights which are able to they're able to take action on. That is kind of for example a 1 meter by 1 meter treatment map for a sectional control sprayer or something like that. And so essentially as we process the data, the volume of data at each stage kind of decreases, but the value of that data increases. So it's sort of distilling out the core crucial information from that data. Another interesting area of this is I mentioned briefly that we kind of like we have to separate out from our data sets a certain amount of data which we want to label, get hand labeled by experts who can say, okay, that's a weed, or oh, that's a wheat plant, or whatever it might be. But we can only ever do that with a sort of very small proportion of the data that we're gathering, because we're gathering so much data from the field. Now, one area that's particularly interesting, sort of as a research area here, is this idea of doing semi-supervised machine learning. So with semi-supervised learning, essentially what you're trying to do is move away from this world where you are just learning from labeled examples. So in the example of RetinaNet I showed, the training process always requires you to have a ground truth knowledge of kind of where the bounding boxes are around your plants. If you can start to make use of that unlabeled data as well, and have the model learn something not only from the labeled data, but also from the unlabeled data, you unlock the possibility of being able to deal with orders of magnitude more data, and potentially kind of gain significantly more insights from that. Now that's interesting for kind of things like, for example, moving from detecting that this plant here is a broadleaf weed to being able to classify what species of weed that is. Because obviously, you know, it's relatively easy to kind of like draw bounding boxes around individual weeds and say that's a weed, and you get a kind of, you know, a good view when you do that of what the distribution of you get your data set is representative of the distribution of weeds in the field if you do that. However, if you want to be able to say spot a particularly rare weed, but one which is you know, potentially quite damaging if it's in the field, then the amount of data you're going to be able to get on that is probably significantly smaller. And so one of the places where I think this is kind of like potentially really valuable is in being able to use kind of make more use of this unlabeled data than labeled than simply the labeled data alone, and that sort of allows us to essentially kind of push our way down this distribution of kind of classes where we have sort of clear imbalance in the different sorts of the types of objects that we're having to detect. So this is a kind of an area of research. I mention it because it's, you know, it's interesting from a research point of view for us, but it's also something which is interesting to the wider machine learning community. And one of the things that's sort of that's kind of potentially very valuable in this sort of operation is we have enormous amounts of this data, but we don't have all of the expertise in machine learning. Out there, kind of, you know, across academia and industry, there's many people who are kind of interested in these sorts of problems. So one of the things which we did last year was to release a data set which was specifically kind of focused on this challenge problem of performing semi-supervised object detection. So we took a smallish set of data that we gathered from some fields, and considered it was about 100,000 unlabeled images and around 1,000 or so labeled images, and essentially proposed this as a challenge problem to the community. And said, okay, if you can, here are some baseline results essentially on what we believe is kind of, you know, a reasonable performance of an object detection model given the labeled data set. And here is an example of how we have taken some existing research and then applied it on semi-supervised learning and applied it using some of the unlabeled data to improve performance slightly. Essentially, now here is your challenge, community, academic machine learning community. Go and have fun with this data set, essentially. And that's a really nice way of being able to interact with the community, sort of give something back to the community, but also be able to kind of benefit from it in the long term as well. Yeah, that's now out there, and there's a data set available which people can go and play with and sort of report results on. And this is, I mean, I don't expect anyone to be able to read this slide in detail, but this is a poster which we presented at a recent conference. So I just want to touch briefly before I wrap up on one specific application, which is you know, of particular interest to us at the moment, because it's something which is kind of top of mind for farmers, and that's grassweed detection. So in a sort of arable crops like wheat and barley, there's you know, broadleaf weeds are continue to cause issues, and you want to be able to control your broadleaf weeds. But there's many ways of doing that. There's the herbicides are kind of available to be able to selectively kill broadleaf weeds, but not the crop plant. Now, grass weeds are more challenging because obviously they are biologically more similar to the crop in question. So there's fewer ways of controlling them chemically. They look a lot more like the crop plant, and they're also kind of very competitive with the crop, so they can cause significant issues with yield. So we took the sort of what we learned from applying these object detection models to counting the actual crop plants and counting weeds, and try to do this again for grass weeds. So it is possible, if you have an expert eye, to be able to spot the difference between an emerging grass weed and kind of early stage wheat crop, for example. And with the resolution of imagery that we're able to gather, where you have around about 4 pixels per millimeter, you can actually spot the grass weeds at a very, very early stage. So the example in the sort of bottom right of the slide is of a emerging blackgrass plant, I believe, in a field of wheat, which is tiny, absolutely tiny, but it is possible to spot it. And if it's possible to spot it for a human who can then annotate it on an image, it should be possible for us to train a model to be able to detect it. And that's what we found, that actually even though these things are absolutely tiny, we've had significant success in being able to spot these tiny grass weeds, which is really quite exciting, because it means that we're sort of, the overall vision of being able to use extremely high resolution imagery to be able to do things which were previously impossible at the scale of a field is now actually it's really, really coming to fruition, and we're able to sort of, we're able to demonstrate this is actually working. And it's going to be hugely valuable for farmers, we believe, because grass weed control, the earlier you spot it, the more chance you have of controlling it. So just to summarize and to wrap up, at the moment, what we're offering in the field is a set of 3 surveys with the Tom robot, and those are focused on, the first one is not doing anything particularly sort of smart from a computer vision point of view. That is just looking for areas of the field which are green. So that's we use the same imagery from the robot, the same process of running the robot over the whole field. But the process of image processing is just kind of say, okay, what's green essentially, and this is sort of for a pre-drill herbicide treatment, for example, to be able to just remove anything that's growing in the field before you plant the crop. The second and third surveys are where we really get into the sort of like the heavyweight kind of models for doing object detection. So here in the second survey, we do broadleaf weed detection, which allows us to generate these herbicide treatment maps, and a crop count where we're counting the individual plants to inform the nitrogen application. And then finally, that's followed up with a third survey, where again we do another broadleaf weed detection, where we can sort of see how the weeds have spread, inform another herbicide application. You're able to sort of, the nice thing about that is that over the course of growing season, you can sort of track the weed population, how it's changing in your field, how weed infestations are potentially spreading or perhaps not spreading. Perhaps the weeds are actually kind of are dying off or being outcompeted by the crop, and that's very interesting to be able to see that emerging from the survey data. And then the final thing is to this plant biomass assessment, which is essentially to predict the overall the overall leaf area of the crop plant in the field, which again informs this nitrogen application as well. So the service is running on farms. We've got 13 farmers sort of running the service at the moment, and significantly more on the waiting list. And we now have been doing this for a couple of years worth of surveys, and can start to see the significant kind of impact on what farmers are able to understand about their field and how they're able to deal with things. So the treatment maps we're providing are kind of providing savings to farmers in terms of their herbicide and fertiliser usage, and we're able to see kind of changes in the field and correlate, for example, the broadleaf weed burden in a particular area, and sort of crop loss, for example. And that's proving to be extremely valuable. So we're really kind of like starting to see the benefits of having these data sets at scale. The other thing I should briefly mention here is that obviously kind of the nice thing about collecting images is that we can, if we store the images for a complete survey, as we develop more models for doing more different, detecting different things, for example, kind of if we extend models to be able to spot, get a better weed detection, or to be able to spot some specific disease or something like that, you can always go and rerun a model over a previous survey and look at how that's kind of evolved, how things have evolved over time. The final thing I want to highlight before I wrap up, and we can move to questions, is just kind of some of the other collaborations we've been working on, kind of where we've sort of kind of working with other partners and sort of research and other partners in industry. So there's one example is the Slugbot project, where we were taking these models for object detection, and instead of detecting plants, we're actually trying to detect the location of slugs in order to be able to control them using a sort of a biomolasticide. So to spray them with a molasticide which is not kind of like a standard kind of chemical based one. The other one is this non-chemical weeding project which I mentioned earlier, which is kind of a demonstration of integrating weed zapping technology with sort of using this essentially large electric probe to go and put a big current through the weeds, and integrating that with the sort of geolocation technology that we have for kind of like being able to accurately locate and go back to those weeds. So those are the kind of R&D projects which show promise for this overall vision of moving to very, very targeted both kind of data about what's going on in your field, more than beyond just what's going on with crops, what's going on with pests and so on, and also targeted treatment of weeds, for example. So that's it for my slides, and I'm very happy to answer some questions now.
Thanks for that, Tom. Yeah, I'll kick the questions off. There's a couple of questions really. What is the typical scanning work rate, hectares per hour? And I understand this desire to keep machines small, but if you want to cover large acreages, what would you do? Would you swarm the robots then?
Yeah, so I mean, there's the modularity of the platform potentially allows us to kind of like to extend the width of the boom, for example, or can kind of like run multiple robots in parallel. We're currently covering sort of 20 hectares in a day with a couple of robots. So it's a significant area already, and something which is kind of essentially horizontally scalable, either by adding more robots or kind of like extending the width of that you're covering.
Because obviously the width, you start going to the traditional tramline widths, then everything just gets bigger and bigger and bigger, and before you know, you've just designed the same machine that is running around the countryside already. Massive weights and massive widths, I suppose. And then the other question was, how weather resistant is the image technology? Is it if heavy rain is in progress, presumably it's going to struggle to scan?
Yeah, so the robots are pretty weatherproof. We've run them in some pretty awful conditions. The robot handlers have some kind of some horror stories about kind of torrential downpours and hail and all the rest of it. In terms of the imagery, obviously, kind of there is variability due to weather conditions, but the really, we kind of like we want to try and make our models as robust as they possibly can be to those different conditions. So the more different conditions we see, and the more examples we have of kind of imagery collected when the weather conditions are less than perfect, the more robust our models become to those sorts of conditions. I mean, the thing about machine learning models is they're only as good as the training data, and so we're always on the lookout for kind of trying to make sure that we've got truly representative data sets that represent the kind of the range of conditions we see in the field. So yes, I mean, obviously it depends on how much of that data you have as to how well the model performs, but in general we've seen that actually kind of it's pretty consistent. The imagery we're gathering is pretty consistent, largely because we've got the kind of extremely good control of the camera heights and of the lighting, which helps significantly. And then weather conditions are a perturbation on top of that, and something which we need to take into account. But we can do that by gradually expanding and extending our training data sets.
Okay, and then my final question was more of a business question: is do you see the scanning service that the small robot companies doing becoming the dominant thing in the future?
I would hope so. It's kind of, it's if we can, what we're demonstrating with the sort of the current cohort of farmers is that the resolution of imagery that we're able to gather, and the consistency of that imagery and the scale of it is very is driving kind of genuine value for the farmers. So they are able to kind of, we're able to produce these treatment maps which are kind of, which then directly drive the saving of inputs. So obviously there are network effects here of kind of like the more that people see this working and seeing it working on their friend's farm, on their neighbor's farm, and so on, the more kind of opportunities we have for kind of scaling this up. But yeah, no, so far the feedback and the enthusiasm and the engagement has been extremely positive about sort of what we're doing. So that's lots of.
Are you a friend or foe of the agronomists then? Because I can see obviously this is a chunk of work that an agronomist would know.
I think we're friends of the agronomists, and in that essentially this is kind of, it allows agronomists to scale their capabilities further, because an agronomist is never going to be able to walk the entire field and cover kind of a full 20 hectares of the field at this kind of resolution. You'll get a sort of W walk of a series of points in the field, which will give you an extremely high quality sampling, but only at those points. Coupling this kind of imaging technology with the expertise of agronomists then allows the agronomists' kind of knowledge and expertise to be able to scale to whole fields. And that's how we see it. And that's very much kind of, we have experts in-house who are kind of have significant expertise in identifying species of broadleaf weed, for example, or as I showed with that grassweed example, of kind of like being able to pick out the grass weeds. And if you can make use of that knowledge and that experience and then scale it, that's really powerful.
Okay, thanks. So I'll let some people ask some questions. Marion, do you want to unmute and ask your question?
Hi, Tom. Can you hear me?
Yep.
So yeah, sorry, I asked my question before you kind of got to the end. I didn't realise it was just the scanning side that you did. I was sort of looking at the whole sort of, given that it's called Small Robot Company, that I thought that you might have on your robots. I've seen robots that do spraying as well. So I was sort of thinking about whether or not you could sort of attach a sort of, I don't know, a roguing device to your robot and solve the problem at the same time as actually discovering the problem and removing it.
Absolutely. I mean, the vision is very much to move in that direction. The commercial service we're providing at the moment is scanning, but we are producing maps which are sort of designed to integrate with existing technology for action, and so that's kind of the commercial offering at the moment. Now, in parallel with that, we do have R&D efforts. So the Tom platform, the robot platform, has this sort of modular nature which allows us to potentially sort of swap in different tools, and the sort of non-chemical weeding project, for example, is sort of an example of doing that in a sort of R&D setting, where we're sort of demonstrating that technology is viable and sort of can work. What we're not offering at the moment as a service is kind of like is doing the action, but that's very much on the road, on the sort of roadmap, and there is active work going on kind of being able to sort of directly take action based on the data that we've gathered. There's an interesting point around kind of taking action, when we want to take that action. Probably depends a lot on sort of what action that is exactly. So, for example, if you're spot spraying, then it makes sense to kind of do the full survey first and then work out what your weed burden is, and then only go and take out as much as you need to, as much spray as you need for the weeds you've got, as opposed to having to sort of make up a tank of spray that you may or may not use if you're doing it kind of on the fly. So yeah, depends on the use case, but I think the idea of separating the survey from the action is potentially quite valuable in many applications.
That's great. Thank you very much.
Okay, Patrick.
Yeah, I mean, you've said that discriminating between cereal crop and grass weeds is tough, but it can be done. I just wondered if you can actually discriminate between kinds of grass weed seedlings, because that might influence your treatment and herbicide treatment, for example.
Yeah, it's an interesting question. We don't have any data on that at the moment. We've been kind of it's so far the sort of the demonstration is for grass weed detection. I guess as a parallel with our broadleaf weed detection, that's also detecting just that it's a broadleaf weed, not what species with the current system. However, we have gathered some data sets where we've kind of, we've got some per species classification, and so I think it's with broadleaf weeds, there's kind of like there's lots of kind of visual cues to go on, especially, obviously once they pull out the cotyledon stage, they're kind of relatively easy to make distinctions for. Grass weeds, I'm not so sure about. I mean, I think with an expert eye and enough data, I think that's probably the crucial thing for the models is if an expert can go in and annotate an image and make a kind of a good sort of distinction and say, okay, that's black grass and that's brome, and can do that consistently over a data set, then there's absolutely no reason why we can't train a model to be able to do that. If a human can spot it in the images, then one of these object detection models should be able to spot it too, and then scale up that effect. However, I don't have enough. I don't know how hard that is as a sort of for a human to be able to do, and so that's probably the limiting factor is can we get enough data to be able to train a model, essentially.
I guess a human might pull it out of the ground and have a look at it closely, whereas a machine might will struggle.
Yeah, exactly. And this is one of the. I mean, if we deal with images, then there's an interesting question around sort of closing the loop. So obviously, with the models, the way they're trained is on images. So the human annotators don't get to go and pick the plant out of the ground and kind of like do a proper analysis of it when they're annotating. However, obviously the throughput is significantly lower, but you can go out in the field and sort of put down a quadrat and say, okay, I'm going to count every single plant in this kind of 25 centimeter by 25 centimeter or 50 centimeter by 50 centimeter area, and then kind of get a ground truth plant count for that area, and sort of do species identification, all the rest of it. But that's obviously very labor intensive, and the scale of data you get from that is probably not going to be enough to train a machine learning model on its own. However, that's the kind of absolute gold standard, is a quadrat on the ground. So one of the things that I think we're very interested in is kind of like essentially trying to sort of close the cycle and go all the way back to that kind of quadrat on the ground truth, and validate that the models that we're building are kind of, actually detecting what's there, and sort of we can say with certainty that we're able to spot the stuff in that quadrat with some degree of accuracy. So yeah, very interesting question, and ultimately comes down to one of just scale of data, because as I mentioned, the problem with these machine learning models is they only work when you have large amounts of training data.
Okay, just got time for one more question. Prad, you want to unmute and ask?
Hiya. I'm working with on the local skills improvement planning on the Chamber of Commerce here in the west of England in Glos, and Gloucester in particular has got, I think, over 70% of the land is, classified as arable. It's going through a bit of a shift in terms of how that land might be used, and a lot of the farmers need to come along this digital journey, and I think a lot of them are on the verge of looking for projects like this to participate in. So I just wondered, are you looking for more engagement? Are you looking for more test sites? What is your current plan in terms of scaling up and growth?
Great question. So we have, we're always interested in talking to potential interested parties, be they farmers or agronomists or whoever it might be. We currently have a very, very large amount of interest in the service, and sort of we are actively working to kind of like fulfill the farmers who are already interested in the service with sort of be able to scale the service up to that level. But it's always interesting to kind of talk to more people and connect with them. We would like to be able to scale this kind of to scale this very significantly over the course of the next few years. And I think that's we are at the moment at the sort of the cusp of really being able to make this go from the 13 or so farmers we have at the moment to kind of like the next step, and then from beyond there we just want to keep on growing and growing. So yeah, absolutely, we're always keen to engage.
And then the other question would be around the actual machines and scaling up. So currently, I guess I'm interested in kind of like how you build the machines and where all the parts come from. A lot of people with your ambitions are locally kind of thinking about circular economies and trying to get their supply chains to be as local as possible, because we want to try and support all the industries locally, and looking across verticals and within, supporting the region. So I just wondered how you're currently building the product, and are there ambitions to try and make them here in the UK, if that's even possible?
Yeah, absolutely. I think the final manufacturing of the robots is currently happening sort of here in Wiltshire. A lot of the mechanical stuff is kind of stuff that's kind of happening relatively locally. There's kind of we have a range of suppliers for different parts. Obviously, some of the more specialized bits like kind of the cameras and so on are obviously kind of more dependent on global supply chains. But I'd say kind of a large amounts of the robot is stuff that's kind of that is kind of done more locally. So obviously, yeah, there's a continuum there. But yeah, especially as we scale, we always obviously want to be kind of as we scale up manufacturing, we need to be thinking very carefully about kind of lead times on components and all the rest of it. And in general, the closer they are, the easier it is to simplifies many things.
Thank you very much.
Thank you.
Okay, so we're just coming up on the hour, so I'll draw things to a close. So thank you, Tom, for a really interesting presentation and taking the time out to do it for us today. It's very much appreciated. I'm sure everybody found it really interesting. I think it's fascinating, some of the things that are coming out of these developments. When the small robot company started, it was all about designing robots, and the scanning service seems to be a really interesting sort of offshoot from it. But anyway, thank you all for joining us today. I hope you will join us for our next lecture on the 16th of May, where we'll be joined by Charlie Rollison from AGCO, who I think is going to talk about technician training, but I'm not 100% sure yet because we've not firmed it up. So it'll be something to do with AGCO, tractors, combines and farm machinery, and it's probably likely to be something to do with technician training. But we'll let you know in due course. So all that's left to say is thanks again, everybody, and we'll see you again next time. Bye-bye.